to get set up, you have to come in and I think just do this course prep quiz. It's real quick. Okay, and one thing I was gonna look at here in order to get into the week 1 assignments, you gotta first make a discussion post. All right, so if you didn't get this quiz, you got to do the course prep quiz real quick. It's a what's called a play posit. One second, and it'll come up like this. And you just play and listen to the video, and she'll have little questions. You answer the questions once you get to them and keep going. I think you've already done that one. So then next, what you'll do is come into module 1 and do a discussion post. Once you've done a discussion post, you can then get into the knowledge check. The knowledge check is another play posit. You just play the video and answer the questions throughout the video. And I think we have to finish those 2 before it'll let you come down to the measurements in linear motion, which is the one we're working on now. Feel free to take your time and walk through lesson 1 and lesson 2. You can email me or call me later with questions if you have any. Then you get in down here, and once you get into, this is the assignment that we're looking at right now, and you'll have to use your DeVry username and password to create the account there for Cengage. All right, and we're working through the problems in that assignment. We've only done the first 2, which are relatively easy, they told me. So actually, no, I'm still on number 2 right here. Okay, so if I use my handy dandy Windows calculator, I have 1520 times 1 divided by 3.281. And I want that squared. Number 3. Certain car has a fuel efficiency at 22 miles per gallon. Express this in kilometers per liter. And I guess now instead of drawing on the board, I gotta use my little diagrams. Okay, so we're just setting up a ratio here. 1 gallon is 3.76 liters. 1 kilometer is 0.621 miles. So we have 2 ratios for the conversion from miles to kilometers. And the second one is for gallons to liters. So a double ratio and times the initial 22 miles per gallon. So on my handy dandy pocket calculator, 22 times 1 over 0.621 times 1 over 3.786 in parentheses. And if you get to where you know how to use the parentheses on this little desktop calculator, it's one of the best calculators there is. Key with this one is the three significant figures in the original number is the three significant figures we have to use in the answer. Number 4, I know there's 8 of them on this first assignment. A surveyor measures the distance across a straight river by the following method, starting directly across from a tree. So you want to make a 90-degree angle with the tree and the water line. That way we get a right triangle and we can use Pythagorean's theorem. He walks 116 meters along the riverbank. That's his x displacement, or how far in the x direction he goes, to establish a baseline. Then he sights across to the tree. The angle from the baseline is 31 degrees. How wide is the river? That would be y in this case, or if you're looking down here in the solution, it's the w. Now, don't ask me why they changed letters. They just did. It's the same distance. The letter there is not going to affect the answer. All right, so we're solving for w. W divided by 116 equals the tangent. So with tangent, we're using opposite over adjacent, right? It's been a while since I've done that. And it just came out, so I hope that was right. Or is that opposite over hypotenuse? Let's see, 116. Yeah, we're looking for the hypotenuse. All right, so given x and the angle, we can then solve for y. So we transpose that equation and solve for w. So I multiply through by 116. So 116 times the tangent of 31 degrees. All right, so first, I think I got to do it this way. 31 tangent times 116. And again, there were 3 significant figures in both of the numbers in the original problem. So we use those 3 significant figures in our answer. Yes, it ends at 69.69. So since we've got to round up to 3 figures, we would round up the 6 to a 7, so 69.7. Again, your numbers may not be exactly the same, but the process is exactly the same. If you're having trouble with your numbers and can't get them to plug in right, just let me know. Nerve impulses in a human body travel at the speed of about 100 meters per second. That's pretty fast. That's how fast pulses run inside your body. If a man accidentally stubs his toe, about how much time does it take the nerve impulse to travel from the foot to the brain in seconds? Assume he's 1.8 meters tall and the nerve impulse travels at a uniform speed. No, he's 1.8 meters, which that's kind of short. That's, well, 3, yeah, a little less than 6 feet. All right, so that's simply taking the distance divided by, or the change in x, divided by the speed. So in this case, 1.8 meters. Divided by 100. A snowboarder on a slope starts from rest, which is 0, and reaches a speed of 1.4 meters per second after 7.6 seconds. What's the magnitude of the snowboarder's average acceleration. So you look at the change in velocity over the change in time. The change in velocity, he goes from 0 to 1.4 meters per second. We start with the final velocity minus the initial velocity, and this is where you start getting into being able to understand these symbols. So if we don't understand these symbols, it doesn't make sense. Delta just means change. So here we're looking at the change in voltage divided by velocity divided by the change in time. So the final velocity minus the initial velocity, or the velocity at 0. So they'll label that two different ways. This one may be VF for final velocity. Sometimes it's just V. Sometimes they'll call this one VI for initial, and sometimes they'll call it V0 for the zero, the 0 point in time when it started. All right, now they got me confused. Oh, because when I divide significant figures, there's a rule for that, and I don't remember it. I know there's a rule for when I divide significant figures. Probably came out with one more than I started with. Let me see if I can pull that one up. Yeah, so there should have been two. Okay, so then in B, we're looking at how far does he go? Did we get A with how fast is he going? Or the average acceleration? And then when we want to see how far does he travel in that amount of time? All right. So another one of those formulas, when you first look at it, you're like, oh my God, what is this doing? But then after you break it down into smaller pieces, it kind of makes sense. What's his initial starting position on the x-axis? That's going to be our 0 reference point. So that's why that turns into 0. Because x of 0, he's starting out at 0. The initial velocity times the change in time. His initial velocity when he starts off is 0. So 0 times any change in time is going to be 0. So the second term goes to 0. The third term, 1/2 AT squared. So we take half of the acceleration that we just calculated times the time that was given to us. So 1/2 of what you calculated in A times the time that was given, in this case, 7.6 seconds, and you square that 7.6 seconds. Don't forget that part. This one's on the outside, so it does get squared, whereas this one's on the inside. It's on the S term, but I'm sure y'all know that. All right, 7 and a tennis player tosses the ball straight up and catches it after 1.3 seconds. At the same height as the point of release. What's the acceleration? Game of toss. Throw it up in the air and catch it. It's going up. Negative 9.8 meters per second squared. Down. When it comes down, 8 meters per second squared. Cool. The square is important because it's not meters per second. It's meters per second squared, so it's going a lot faster. All right. And I'm hearing you rapping. While it's in flight, yes, that's because of the way they asked the question, while it's in flight, meaning while it's going up, it's 9.8 meters per second, but in the downward direction. The ball's going up, gravity is pushing down. So the acceleration is in the opposite direction of gravity. That's why it's negative. What's the velocity of the ball when it reaches its maximum height? This is an easy one. Once it gets up here, it comes to a dead stop before it starts to fall. 0. It's 0 meters per second at its maximum height. And at that point, there's no direction. It's at a dead standstill. All right, now what we have to calculate the initial velocity of the ball. Seven C. All right. Consider the equation, the change in the y direction is equal to the initial velocity times the time. Again, this is a sentence. So if I look at this as a sentence and I read it that way, it makes more sense. Whereas just looking at the hieroglyphics of it. So we take the initial velocity times the time plus 1/2 times the acceleration times the time squared. We know the acceleration. The change in the y direction total is 0. Because it ends up where it starts out. So the equation has two solutions, one at t equals 0 and t equals 2 times the initial velocity divided by gravity. So when t equals 0 and when t equals 2 times the initial velocity divided by gravity, those are our two answers. If it's caught at 1.33 seconds, then we just solve for the initial velocity. Acceleration times time divided by 2, 1/2 at squared. It's that same formula. It's just the way they write it. 1/2 at squared. Um, 9.8. That's our acceleration due to gravity close to the surface of the Earth. You watch the little video in a few minutes. It's only that way right here at Earth. If we were on another planet, that number would be different. If we're higher up in the atmosphere, that number would be different. But because of where we are, it's 9.8 meters per second squared. All right, so we took this and we solved it for the initial velocity. We need to look at the conversion of that equation. That is not a necessarily easy one to convert. All right, ball's thrown directly downward with an initial speed of 7.15 meters per second from a height of 29.9 meters. Again, 3 significant figures in both those numbers. After what time interval does the ball strike the ground? Upward is the positive y direction, and y equals 0 at the point where the ball is released. Your initial, instead of the initial velocity being 0, now the initial velocity is negative 7.15 meters per second. Acceleration in the y direction is negative g, so we end up with negative 9.8 meters per second squared. I was given the change in y at negative 29.9 meters. Then they take this formula and take the square root on both sides. So here we go again, where one of them is squared and one of them is not. One of them is in the units and one of them is in the number. So if I'm multiplying this out, 7.15, that gets squared. Plus 2 times 9.8, that does not get squared. The square is in the units. So you square the initial velocity, you do not square the 9.8.